we have set our motivation, we have got into the introduction about algebraic topology. So now let's get back to business. So in the beginning I told you that I am going to redefine or relearn some of the aspects of electromagnetics, particularly the parameters, using the new set of tools. So we will start looking into the basic definitions. So let's start with the theoretical framework. So what we have initially is the idea of source and configuration variables. So what I mean by that? So let's take the simple example of Lorentz force. Let's look at the slide here. This we know from our basic electromagnetics lectures, that if it is purely static field, the force is purely an electrical force. If it is a moving charge, then we also have a magnetic force. In the case where we have both, so the total force will be given by the electric force plus the magnetic force. But there is something specific about this equation, what we call as electric field and magnetic field. The normal way in which we used to talk about electric field, so this is something we need to look into much further. So when we look at electric field, we always assign electric field to E, but when we look at magnetic field, we use the letter H to define magnetic field strength, to be specific. But the physicist community, they might always use the letter B to use magnetic field. There is a reason for that. The reason is very simple. Whatever field that is related to force, they are called as the intensity fields normally. So in the case of electric field it's the E, and in the case of magnetic field it's the B. So that's the reason why we have the E and B as the configuration variables. So we call them configuration variables because they are related to the charges. In other words, if you can call a term which is magnetic moment, so magnetic moment is given by the product of pole strength and or distance of separation between the pole. Let me explain this further. So assume that we have a magnet where there is this north pole and a south pole. So let us say the distance between these two things is given by L, and the pole strength, individual pole strength, is given by P. So we can write the magnetic moment as the product of the pole strength multiplied by the length of separation. So this is the basic definition of the magnetic moment. So accordingly you can get the value of a pole strength, how much strong or what is the strength of a pole. So that is what we are using here. So what we are using here is pole strength to define the magnetic field. Obviously if you look into literature, they won't define magnetic field, particularly the B, they will call B as the magnetic flux density, and they will define it in a different way. But in the case of algebraic topology, we are going to define B as the force acting on a unit pole, assuming like that. Similarly, the electric field will be defined as the electric force acting on a unit charge, and this is the definition for the configuration variable. The configuration variables, as I have told you, are variables that are related to the charges of electric or magnetic field. So that being said, let us go further a bit. We can have also, so this we have looked into it, so we can also have something called as source variable. Again here I am using only the magnitude. this equation is not valid if you are using also the direction. So we are only interested in the magnitude. So in the case of D, we know that it is the charge contained divided by the surface area. In other words, what we are doing here is assuming that there is a surface and there is a charge that is inside, and the surface area is and the surface area of this closed surface is given by S. We know that the electric flux is equal to, so we will call the electric flux as phi is equal to integral d dot ds. So what we get is, under the condition that we can go into a very small surface, the value of d will be the flux density, where S is the surface area. So this is the way we have been defining fluxes, and this is nothing but the charge contained inside the closed surface. So you can see here I have used the term magnitude only because I want to associate D and H. Similarly, H can be related to the magnetic pole strength, what we have defined here, divided by the surface. A word of caution to be exercised here. As I told you, the engineering community is not used to B as magnetic field strength and H as source or configuration variable. We have been taught to use H as the magnetic field strength and B as magnetic field density. I have tried to use a different terminology. Obviously this is not something new. If you look into people like Arnold Sommerfeld or Richard Feynman or people who are physicists, they have always argued in favor of calling B as the magnetic field strength. So in either case it does not really matter to us. What we are doing now is setting the basis for using the right topological association for those field quantities. In fact, we will not even need those field quantities, I told you before, but we have to set the right foundation to associate them, and you will see the reason why we are doing that in our next slides. We have used the word source variable and configuration variable. Source variables are directly related to the sources, and configuration variables are force that are created due to those electric and magnetic forces. So in the case of the source variable there is no force association, but in the case of configuration variable there is always a force association. So that is the starting point where we are going to begin our topological understanding of those field quantities. So I have been using the word topological several times. What is the difference between geometrical and topological? Geometrical means there is some amount of, or in fact a metric associated with anything that we model. So if you say we are geometrically modeling, the metric is always important, whether we are in millimeter or micrometer or picometer or meter. So there is always a metrical association. But in the case of topological, we do not have any metrics attached to it. It is purely the manifold itself. So when we are talking about a one dimensional or a two dimensional or three dimensional space, for example, a point is a zero dimensional object. A line is a one dimensional object. Any surface is a two dimensional object, and let us say you have a volume. It need not be a tetrahedron, any volume is a three dimensional object. So depending on where we are in the dimension, so they are going to have certain association, and there is also not only that, the electric field and magnetic field and also other quantities, they are going to be associated with geometrical object. That is what we are going to see in our next slides. So when you see a point association, what we call here phi is nothing but electric scalar potential. So the electric scalar potential is defined on a particular point. It does not make sense to define a potential along a surface, along a volume, because it does not make physically sense. A potential is defined at a point. Similarly, we can talk about V and U. As I told you, we are going to use a different, in fact a right term to define V and U. In most of the engineering literatures, we use the word electromagnetic force, which is questionably not the right way of putting it, because this is not a force term. There is no, the unit of this is not Newton, but we kept using it because in the historical time we normally use the word force, because force is the basic quantity. Later on came energy, and later on came field quantities. So they were talking about force at a distance. They do not know what is that. So when they associated something, they said it is a force at a distance. Similarly, they have been using the term electromagnetic force because they thought it is a force term, which is not the case, but still we kept using it because we got used to it. Sometimes for people who find it difficult to accept it as force, they still kept using the term EMF because they do not need to say the word electromagnetic force. But again, this is fundamentally wrong. So when we are using algebraic topological method, we are going to use the term electromotance. So what we call as electromotance is nothing but the line integral. So V is equal to the line integral E dot dl. So this is the electromotance. This is a term that is well known but not used, because we are being used to use the word EMF. So this is actually the same, but we will not be using the word EMF and we will be using the word electromotance. So electromotance is associated with the line, like the case where we had the case of potential, which is associated with points. So in the case of electromotance, the association with respect to line, and the other one is called as magnetomotance, which is the counterpart. Basically the counterpart is U equal to integral H dot dl. So these are dot products because they are all vectors. So here the normal term what we will be using is magnetomotive force, but which is actually the right term that should be used is magnetomotance. So magnetomotance, and we will not use the word EMF or MMF, and we will stick to the terms electromotance and magnetomotance. Obviously we did not do this in the earlier lectures because we did not have the need to associate the topological dimension to each of these quantities, but in the case of algebraic topology it is fundamental to begin with the right definition. So the unit of the electromotance is volts, and the unit of magnetomotance is amperes. So that being said, let us go to the next one. So we have covered the point association, we have covered the line association. Let us look at the next one, which is the surface association. The surface association also has quantities which are in most cases properly represented. We only make the mistakes normally in the case of V and U, but we have the right terms for the different fluxes. So the first flux what we are going to talk about is something that we already saw, is the electric flux, which is equal to integral d dot ds. Again, it's a dot product, they are all vectors, and this is related to the surface. So this is the electric flux. The next one is magnetic flux, which is written as capital Phi integral here you can see the values are it's also associated with the surface, and this is the magnetic flux. So normally we use the term electric flux and magnetic flux in the right context, so we are not going to worry about it, and the important thing is these are all scalars. So phi is a scalar, and also in the earlier case where we had V and U, they are also scalars. So we have covered electromotants, magnetomotants, electric flux and magnetic flux. So there is another thing that is associated with the surface, which is something that we all know, and the most familiar one is the current. So we call it I is equal to integral J dot ds. J is the current density and I is the current. So the unit here is amperes, and here we have J, that is ampere per square meters, and here we have the value of the surface, so it is associated with the surface. So that being said, we have covered all the surface association. So there is something missing, which is the volume association that we are going to see in the next slide. So in the volume association we have a quantity which we call it as Q. So Q C is a charge content. So the charge content is equal to integral rho dV. So rho is the volume charge density multiplied by the volume. Please pay attention that this is not a dot product, they are both values are scalars. So here the association is with respect to the volume. So again I and QC, they are scalars. So with this, what we have got is the basic definition of electric field, magnetic field, and electric flux density, magnetic flux density, all measured or all represented by the scalar counterpart. These scalar counterparts are the most fundamental things that we will be using. So we have 1, 2, 3, 4, 5, 6 and 7. So what we have got here is the field variables are physical quantities and they are associated with line, surface or volume density of another variable. So for example, electric field is the line density of electromotors. So voltage difference actually, and magnetic field is the line density magnetomotives. And similarly, D, the electric displacement, is the surface density of electric flux, and B is the surface density of magnetic flux. So this is V, this is U, this is phi, and so on and so forth. So in fact, the most important thing is we are not used to think of electric field as a line density or the electric displacement as a surface density, but in fact they are what they are. So they are the line densities or surface density, and in some case it is also volume density. For example, when we talk about rho is the volume density of charge content. So if we understood this, we are able to understand all the quantities, basically all the field quantities E, H, D, B and rho, they are all densities, whether it is line density or volume density or surface density, it does not matter, they are all densities, and they are all defined locally in a point. So there is, when you say E, you are defining E at x comma y comma z comma t. So these are the point definitions. So they are all locally defined in a point which is defined by x comma y comma z, and they are all vectors. I told you they have a particular magnitude and a particular direction. So with this we are able to understand that the field quantities are fundamentally line, surface or volume densities. I mean, the main point here is they are associated to points but not associated to the fundamental topological objects they are. We are associating all of them irrespective of their topological association to a particular point in space and of course in time, and they are all vector quantities. So the counterpart of it, which we already discussed, are the global variables. I use the word global variables cautiously because in some cases we can also call them as integrable variables. I do not use the word integrable variables for the simple reason that when we look into the point association, it is difficult to, or in fact it is not possible to talk about integration of a point. When you have a line, you can integrate it along the line. When you have a volume, you can integrate it within the volume, or if it is a surface, you can integrate it along the surface. But it is a point, it is very difficult to integrate. So that is why all integrable quantities are also global quantities, but not all global quantities are integrable. So in the case where we have phi, which is the electric scalar potential it is not integrable, not inter. So that is why we use the term global. Global quantities. So what are these global quantities? The global quantities, they are not something. What they are not? They are not line or surface or volume densities of any other quantities. So this is the basic definition of what is a global quantity. The global quantities cannot be defined as line, surface or volume densities of any other quantities like the way we have done it for the field quantities. They themselves are integrated along the topological space where whatever they are associated to, and they are not defined on the points. Like in the case of field quantities, they are all defined on a particular point, but here the global quantities are associated or defined over the domains. If it is associated with a point, the point is the domain itself, like in the case of the electric scalar potential. Similarly, the electric flux is defined on the surface, and these are the domains. They are not line, surface or volume densities of any other variables. They are all scalar quantities as compared to the field variables, which are all vector quantities, and they are all defined on the volumes, surfaces or lines and points, which are the domains which are associated to those particular global variables. So this is the basis of the global variables. So with this we have formed some basic understanding and also the terminologies that we need in the next step for associating them in an algebraic topological manner, but we have now covered the basic definition of those quantities that we will be using. They are all scalar quantities. We are not going to use any of the vector quantities, and those scalar quantities are associated to certain domains. With this we will end this module, and when we go into the next module we will look at the algebraic topological framework. Thank you.